Hello, and welcome to Lecture 13, Part 1 for Life in the Universe. In this lecture, which will consist of 3 videos, we will continue into Unit E, and we'll complete Unit E after the third of these videos. And we're going to, in this video, continue with our look at light. In particular, 2 things we want to look at here, the electromagnetic spectrum and thermal radiation. So this, however, being the first video of the lecture, we've got an alien, and this is maybe the one I'm the least familiar with, but I think they look pretty cool. This is from Stargate Atlantis, a show that I probably only seen a couple of episodes of. The show Stargate SG-1 I've seen a bit more of, and I saw the original Stargate movie. But anyway, within the series, I know these were called Race and were one of the primary antagonist of the series. And I guess at some point I'll probably watch more of the old Stargate stuff and get to know them better. If I'm not mistaken, and I could be wrong about this, maybe misremembering this, but I think Jason Momoa may have been in the show before he got to be all famous. Anyway, I'll have a link in the description if you want to go listen to the soundtrack to it. All right, now, when I'm sure you all know this, that if you send white light through a prism, that white light is broken up into all these pretty colors that we call a spectrum. And this happens because light of different wavelengths goes through the prism at slightly different angles. And color is how our brain perceives differences in wavelengths. And it turns out the short wavelength end of our vision, down here around 400 nanometers, is kind of the blue and violet end. And the long wavelength end around 700 nanometers is red. Now, the general wavelength scale along here wouldn't be quite linear. 500 nanometers would probably be about right there, 550 about right there, 600 about right there. I won't try and actually write the numbers here for you. Now, we commented earlier about how there's only this very narrow range, less than a factor of 2, approximately, in the wavelength range of the light we can see. And that there is more to light than meets the eye was discovered in the year 1800 by William Herschel. And he's a person of quite some importance in astronomy. He was born in Germany, but immigrated to England as a young man. I think he might have still been in his late teens at the time. And he worked for a while as his day job was as a composer and an organist. And he did astronomy as a hobby. And then in the year 1781, he discovered the planet Uranus. This was a really big deal because this was the first time in recorded history that a new planet had been discovered. Herschel wanted to name Uranus something like Georgium Sidus, which is Latin for George's star in order of King George III, King of England at the time. And it's probably good the mythological scheme for naming planets prevailed because 1781 was during the American Revolution, and George III was not very popular, say, around here, Massachusetts at that time. Anyway, the king was sufficiently impressed by this that he gave Herschel a generous lifelong pension, and all that Herschel had to do, his only duty, was that if the king dropped by with some friends, to let them look through the telescope. That is an astronomer's dream job. Anyway, he went on to basically devote his full time to astronomy after that. Out the window here in this painting, you can see his really big telescope, and we're going to see later in the course something he did with that. But what concerns us here is what's in the foreground. So he was trying to measure the amount of energy in sunlight and different colors of it. So he blocked up this window except for this narrow slit where he put a prism. So the sunlight coming through would be spread out into the colors of the spectrum that you see here. And then you might recognize what's here on this wooden frame, these little glass tubes with bulbs at one end. Those are thermometers. So what he could do is he could move this one into different colors, see how much the temperature went up, and from the others out here out of the sunlight, he could use as a control. And what's particularly important for us here right now is that when it was in the position shown, where this thermometer was near but not quite in the red sunlight, the temperature still went up. And Herschel correctly interpreted this as being due to light that was invisible to the human eye, but was still causing the temperature of the thermometer to rise. And what he had done, in fact, was discover what we now call infrared radiation. Now, so right here, we've got a little view of schematic of the electromagnetic spectrum with wavelength increasing from left to right like that. So shorter to longer wavelength. And that means that frequency and photon energy increase from right to left, so going that way. Now, note that the wavelength scale is logarithmic. Each step along here, the wavelength is then a factor of 10 larger than the previous one. And even though presumably it could go to both directions a good bit further than what's shown here, 10 to the minus 5 nanometers that we have here is, that's 10 to the minus 14 meters. This one right here would be 10 to the 4 meters, 10 kilometers. So that is a factor of 10 to the 19 range and wavelengths that's shown here, a 1 followed by 19 zeros. So out of this 19 orders of magnitude plus in wavelength variation among electromagnetic radiation, a tiny little bit of it where it varies by about a factor of 2 is all that our eyes can see. Now, it's not very important for us to know exactly where these boundaries are. They're somewhat arbitrary anyway. But it probably is good that you know the order they come in, I guess. I want to say a little bit about each part of the spectrum outside of visible light, starting where Herschel started us with the infrared. Infra is Latin for below, so this means below red in frequency and photon energy, longer wavelength. And as we're going to see shortly, things at typical surface temperatures of the Earth, including you, emit a fair bit of infrared radiation. We often use the term microwaves for this kind of transition between infrared and radio waves. So actually a lot of radio communications, including cell phone broadcaster frequencies are actually in the microwave part of the spectrum. And your microwave oven works by zapping the food with microwaves at a frequency that water molecules will absorb. And so that means the water molecules will absorb that energy and heat up your food. I'll also mention, I probably should indicate something a little bit more in here, this region right around in here is often also called the submillimeter. Longest wavelength electromagnetic waves we call radio waves. Not only for communications, but these are also used for radar. So where you send a pulse of radio waves to bounce off precipitation or aircrafts or even near planets. All right, in the other direction, you probably know what UV stands for. That's ultraviolet. Ultra means above, so this is above violet in energy and photon energy and frequency, shorter wavelength. When you get in the ultraviolet, the photons start to have enough energy to potentially damage some biological molecules like DNA, which is why you should limit your exposure to direct sunlight. And it's also why you should never use a tanning booth unless you want to have skin cancer. X-rays, more energetic still. You have to be more careful with them than the UV. But still in low doses, occasionally X-rays can be more beneficial than harmful. And that's because they'll go through you, and it gives a way to medically figure out some things about what's going on inside you without having to cut you open. And one thing I can tell, I'm very happy about X-rays technology. I think it was in 2009 I had an abscess tooth, which if you've ever had one, they're quite uncomfortable. And but the pain wasn't very well localized. So I could really only tell it was one of maybe three teeth that were, maybe four of it was hurting. And I guess my dentist could have done exploratory drilling to find the infected one. But instead, he took an X-ray, and on the X-ray, it was immediately obvious which one was infected. So I only had to have one tooth had to get a root canal, and not three or four. And then finally, the lowest energy or shortest wavelength, highest energy, um, highest frequency electromagnetic radiation we call gamma rays. Basically, no level of gamma ray exposure would be considered safe. And gamma ray exposure will not turn you into the Hulk. Stan Lee had said that at Marvel Comics, when they were creating the Hulk, he and the other writers didn't really know that much about gamma rays, but it sounded cool, so that's why they used it. But in real life, instead of turning into the Hulk, Bruce Banner would just be dead. Now, it makes sense that visible light is about the range that it is because our atmosphere is transparent to that part of the spectrum, and the sun puts out most of its energy as visible light. But there's no reason why it has to be exactly the range that it is. And indeed, other animals see somewhat different wavelength ranges. In particular, many insects see further into the ultraviolet than we do. And so as an example of that, on the left, there's a photograph in visible light of a flower, which is all nice and pretty and yellow. But in general, I don't really see any other patterning to it. It just looks yellow to us. Well, the other two pictures were taken with ultraviolet cameras and then shifted to visible light so we could actually get some idea of what they look like in the ultraviolet, simulating the way bees and butterflies would see it. And you can see in the ultraviolet, there is some additional patterning, especially the center of the flower looks different from the petals. And presumably the bees and butterflies see that and are attracted to it. You've probably noticed that for a lot of insects like flies, if you get them in a room during the daytime, that they often spend a lot of time near the window. And if it's a room with fluorescent lights, they might spend a lot of time around those fluorescent lights. And that's because something about related to the fact why our sky is blue. And as you can see, if I point my camera up here towards my window, I just happen to be recording this particular one at night, but I will try to arrange for the sky to be blue when you watch this so you can look out and remind yourself of what a blue sky looks like. But the reason the sky is blue is that our atmosphere actually isn't entirely transparent, but it scatters some of the sunlight that comes through it. And that scattering is more efficient at short wavelengths. So blue light is more likely to scatter and bounce around a time or two before it gets to our eyes than red light is. And that's what gives our daytime sky that bright blue color. In the ultraviolet, that's even more effective. So if you could see in the ultraviolet, the sky would look even brighter. And apparently a lot of flying insects by instinct fly towards ultraviolet light because normally that means there's open sky and they can fly that way. Fluorescent lights put out some UV light, which is why they're attracted to that. And the window, they're seeing some of the UV coming through the window and probably wondering why that big invisible force field is there and they can't get through it. And of course, sometimes this also leads them to their dooms at bug zappers. Now, before I go to the next picture, a word of caution. It's a picture of a snake. And I mention this because some people have an extremely strong fear of snakes. Very deep-seated. My mother was such a person. She could not stand to see a picture of a snake in a book or see a snake on TV. And in fact, once, maybe about 2-3 years before she died, she was inside her house and she looked out the window into the backyard. So she's inside the house and she saw a little snake, probably a garter snake, in the backyard. Okay, she's inside, the snake is outside. She went and hid in a closet in her house for a while until the snake, she was confident, had gone away. And after that, for the remainder of her life, I don't think she ever set foot off her back porch into the yard. I suspect this is something that is kind of instinctually hardwired into the primate brain, because one thing, it is good to be cautious around snakes you don't know, but also there would have been a time in our distant ancestors where snakes would have been among their primary predators, and I guess particularly strong versions of this sometimes surface. So anyway, if you react to snakes the way my mother did, you probably don't want to watch the next couple of slides. But for the rest of us, I'd like to introduce you to Lumpy. Lumpy is a banded rock rattlesnake. And I don't know Lumpy personally, but the website where I found his picture said that's what his name was. All right, well, if you know much about snakes, you probably know that rattlesnakes, along with copperheads and water moccasins in North America, are part of a group that we call pit vipers. And that's because of an organ on their head between the nostril and the eye that we call the pit. Now, Lumpy's nostril, he breathes through that, just like we do. There's Lumpy's eye. I don't know much about rattlesnake vision other than the wavelength range is probably pretty similar to ours, although not quite the same. And probably the color vision's not as good. Primates have particularly good color vision compared to most vertebrates, and including compared to most mammals, although some birds have significantly better color vision than we do. And then right here in between the eye and the nostril is the pit. And the pit is a crude infrared eye. Good enough to be able to tell that there is something brighter in the infrared over in that direction, but not good enough to say to read by it. So it doesn't give a really sharp image, but it can tell there's something over there that's emitting more infrared than the surroundings. And why would that be useful? And for that is we come to the concept of thermal radiation, or also black body radiation as it's called. And this is something that happens because anything that is warmer than absolute zero, in other words, anything, will emit electromagnetic radiation just because it's warmer than it could be. Calling it thermal radiation, I think, should be fairly obvious. Why we call it also black body radiation might not be so obvious. I'm going to hop out of the share for a minute. And I'll just hold up here my calculator case here, which you can see is black. And say compare it to the shirt I'm wearing, which, well, that might look kind of black. It's actually navy blue. It's dark blue. Well, actually here, let's see. Yeah, no, here. Okay, the stapler here is blue. This is a better blue here. Okay, now the reason why the stapler looks blue is the dyes that were mixed in with the plastic when it was being cast are very good at absorbing visible light that isn't blue, but it reflects some of the that blue light. So the light that bounces off of it into my camera and then reconstructed digitally from your screen in your eyes is blue, but that's reflected blue light. Okay. When something looks black, like my calculator case, that's because it's very good at absorbing across the entire part of the visible spectrum and doesn't reflect very much. Now, I have no idea what its reflective and absorbing properties are in other parts of the spectrum. I'm pretty sure gamma rays just go right through it. But you know, maybe it's a perfect mirror in the infrared. Probably not, but it could be for all I know. All right, well, if you imagine an idealized object that absorbs perfectly across the entire spectrum, doesn't reflect anything, then all of the radiation we see coming from it would be thermal radiation. And that's why the term black body radiation is also used here. So what this plot shows is for some arbitrary units of intensity, the intensity as a function of wavelength for 3 objects in thermal radiation, one at a temperature of 3,000 Kelvin, so a relatively cool star, one at 6,000 Kelvin, so about the same as the surface temperature of the sun, and one at 12,000 Kelvin, a reasonably hot star, and wavelength here in nanometers. Visible light indicated here. So that means that over here is where we would have the infrared, and over here would have the UV. I didn't make that U look very U-like on this side. All right, now, two things to notice about these curves. One is that as long as we are talking about objects of the same size, because a bigger surface area for bigger objects will let them emit more, but as long as they're the same size, a hotter object emits more than a cooler object does at every wavelength. And the other thing to note is for the hotter objects, that peak in the wavelength moves to shorter wavelengths. So at 3000 Kelvin, like I said, surface temperature of a cool star, so at about 1,000 nanometers, that'd be near infrared. So it's mostly putting out infrared. Although you can see here, it's putting out some visible light. And in fact, that would appear to be glowing red to us. For something the same temperature as the sun, most of what it puts out is visible light. It puts out a fair bit of infrared and some ultraviolet as well. And note the peak is in the middle of the visible part of the spectrum. That's why the sun has kind of a yellowish look to us. Something at 12,000 Kelvin is mostly emitting ultraviolet light, but it's emitting a lot of visible light. And you can see because it's most of it is here at the short wavelength end of visible light, that would appear to have a bluish glow to us. Now, at the temperature of, say, a warm-blooded animal like a human, that peak is somewhere around maybe around 10,000 nanometers, a little bit less maybe. So what we might consider the mid-infrared. And our surroundings are also emitting infrared radiation, but because we're a little warmer than our surroundings, we're a bit brighter. And that's the wavelength region where Lumpy's pit is most sensitive. So that helps Lumpy find little warm-blooded critters in the dark like mice that Lumpy might want to snack on, because that mouse will be brighter in the infrared than the surroundings. So if you ever find yourself at a room with a rattlesnake, don't try and hide from it by turning the lights off, because it will still be able to see you through your infrared radiation, but you won't know where that poor frightened snake is. All right, so that gets us to the end of this video. And I thought kind of a cool attendant secret code, even though probably can't read much of this here. Up at the top is actually a little bit from the star catalog that's in Ptolemy's Almagest, which apparently was actually not Ptolemy's observations. It was the observations done by Hipparchus in the 2nd century BC, so about 300 years before Ptolemy. Ptolemy just basically republished it. And then there's an English translation of this kind of list of 4 stars all in the constellation Virgo, and which stars a modern designation has been identified with. But it's actually, as being indicated, is they're supposed to make a quadrilateral, and these 4 stars don't actually make a quadrilateral. However, if you look at where the planet Uranus was around the time Hipparchus would have been observing in the 120s BC, and Uranus is barely visible to the unaided eye. It turns out that based on the positions that Ptolemy gives for Hipparchus's catalog, that if you have, let's see, here, here, and here are the other 3 stars, and then right about there where the 4th one, during the time when Hipparchus would have been observing, Uranus would have been in that part of the sky. So this seems to be a pretty good argument in the favor that Hipparchus actually spotted the planet Uranus 1900 years before Herschel did, but he just thought it was a star. And there are other definite observations of Uranus before Herschel recognized that it wasn't a star. And it's for that reason that Herschel still deserves the credit for the discovery of Uranus, because even though other people may have seen it before he did, he was the one who realized it was a planet. And that's why he gets the credit for the discovery. But anyway, our code is Hipparchus and Uranus, since Hipparchus apparently did spot it. At least this seems to be pretty good evidence that he spotted it in almost 2,000 years before it was officially discovered. All right, so that's the end of this video. In the next video, we'll go on and continue taking a look at some properties of light, and I'll see you there.